Alright, now we're looking at the second area of study in lesson in Unit 2, I should say, and that's titled How is Radiation Used to Maintain Human Health? That you can think about that as nuclear medicine. Alright, so first of all, what is radiation? Alright, so radiation is an interesting definition of it that's in your notes there. There's many forms, so it's emission of energy. Alright, that's the missing word. As electromagnetic waves, as waves, or subatomic particles, subatomic particles, especially hot, and this is the other missing one, high energy particles, and not just any ones that cause ionisation. Alright, so an ionisation there is critical, so two words missing in your notes, those two there. And the ionisation, is, as I said, is the critical one, because if it ionises things in your nucleus of your cell, then it can affect the nucleus of the cell and what it's supposed to do. Well, we'll get to that more often. So, we've got a little bit of a diagram here. And this is in your notes, so here we go. So we start up the top there with radiation, and so we then split into two. So it's the waves. Now, I wasn't specific in there. In my notes I was specific, but I wasn't specific in what I wrote on the reasons page. So it's electromagnetic waves, or particles. So if we look down the electromagnetic wave side, we get the electromagnetic spectrum, which is broken up into a whole bunch of different wavelengths and associated frequencies, all the way from radio waves on the end, visible light that allows us to see things, microwave in there that heats our food up, infrared night vision goggles and stuff like that, ultraviolet gives us skin cancer, X-ray we can look at broken bones, and then gamma rays down the end. Alright, so then there's some particles. So there's a bunch of other subatomic particles, and then there's neutrons, there's cosmic rays coming from outer space, then there's radioactivity, which is beta, alpha, beta, and gamma. Alright, so there are our different radiations. Alright, so let's have a look at the first one that we're going to look at, and the first one we're going to look at is X-rays. Alright, so in your notes there, it says 1895, bloke named Wilhelm Conrad Rontgen. He was studying these things that were called, that they newly discovered, and they were called cathode rays. And the reason they're called cathode rays is because they come from the cathode. And they were produced inside a glass tube. But what he noticed is, he was looking over here, and then there was this screen over here, and what he noticed is whenever these cathode rays that they were doing, looking here, this screen would glow. And when he turned it off, the screen stopped glowing. So, and that, the missing word there is glow. And so that was quite interesting to him, that would would happen. So you were saying, oh, well, there must be some sort of rays that are going from over there to there onto the screen. So, and because he didn't know what they were, didn't know at that time they were from electromagnetic spectrum, he called them X-rays. What we now know, of course, about X-rays is that they are electromagnetic waves of a particular frequency, and they are, this is missing, high frequency, short wavelength, and so, as it says in the notes there, from 0.001 nanometers to about 10 nanometers. Alright, so it's not in the visible light region. Visible light region's nanometers, but it's hundreds of nanometers. And the other thing, because of their high frequency, what that high frequency leads to is for them to be able to penetrate flesh. And in one of the videos that's there on the website, there's they go through some good stuff about in the early days after X-rays were first discovered, you know, like carnival sideshow kind of things. People go and stick their hands and feet in these boxes and see their bones, etc. Because it penetrated flesh, but not dense stuff like bone, and so that's, for us, that's quite useful. All right. Now, of course, back in the day when they were using it on the, you know, in the carnival sideshow kind of stuff, they didn't realise what overexposure problems would cause. All right. However, as I've said, they penetrate flesh but not bone, and so let's have a look at some. All right. So here's some examples of X-rays. So the top one there is X-ray of a hand. So you can see that. You can see, you know, over here and in here and in here, you can see, you know, real light stuff there. So that would be, you know, fleshy things. But then in the bones, you can see the bones, and also you can see a little bit about where the density of the bones too. All right, and here in the wrist there, you can see all the individual bones and all that sort of stuff there in the wrist. But what's most interesting is here, and this is the same hand, there you can see a little dark spot. So the little dark spot is where the X-rays are not absorbed, and so that means that bone's broken. And also, so in the fourth metacarpal there, so the metacarpals are in the hand, all right? So they're in the hand. So yeah, your wrist is this bit here, your hand is this bit, and then your fingers up here. All right. Now, that's what I was going to point out, and you'll notice the fifth metacarpal here, it's got a bit of a woof in it, and you can see in the middle here, it's got a little bit of a more denser spot. So, so around there, and so that fifth metacarpal's actually been busted at some point in time and then repaired itself. So that's this end here, that's where your little finger is. Alright, so there's that. Then there's some dog that swallowed someone's car keys there. You can see the car keys. And then the last one's a very interesting one. This one here, that's actually a finger. And as you can see, it's very interesting because it's got two dislocations but no breaks. So that's very interesting, that one. All right, so you can use X-rays to, you know, see inside the body. So it's quite handy. All right. So that leads us, because they are electromagnetic waves, then the wave equation, V equals lambda F, the wave equation holds. Now, in the case of X-rays, the speed of light, the speed of electromagnetic waves is the speed of light, which is c, and that's 3.00 by 10 to the 8 metres per second. So all electromagnetic waves, of which light and X-rays are, all travel at what we term the speed of light. Lambda, of course, is in metres, frequency, of course, is in hertz. Alright, so we can use the wave equation to calculate some things about wavelengths and that of X-rays. So let's have a look at an example. Alright, calculate the wavelength of X-rays that have a frequency of 2.75 by 10 to the 19 hertz if they are travelling in air. Alright, so V equals lambda F. And V, as we've already mentioned, is the speed of light, speed of electromagnetic waves, lambda times the frequency, which is 2.75 by 10 to the 19. If you then divide both sides by 2.75 by 10 to the minus 19, you get 1.09 by 10 to the minus 11 metres. Alright, and so light is is not quite as short as that, so it's shorter wavelength than light. Alright, then just underneath that little it's a little short sentence, effects of overexposure. And I already mentioned the effects of overexposure. They weren't known. Alright, well, not known for some time. And that's the missing word there in your notes. Okay, so, that's a matter of you don't know what you don't know. And because they were just discovered, they didn't know what the effects were going to be. But now we do know that living tissue doesn't like too much X-rays. They're great, as we've seen back here in these, they're great for us being able to have a look and see what's going on. But we don't want to be overexposed, because then our increases the risk of something happening to our tissues. Alright, so how do we produce them? Alright, so what do we do to produce X-rays? So in your in your notes there, I'll come back to the words that are missing, because I want to use I want to use this diagram that's there. Alright, so how do we produce X-rays? Well, basically, it's a very specific apparatus, and there down the bottom there, that's what it looks like. So it's this glass tube with which has got a vacuum, and you can attach a potential difference to both sides. And so what you do is you get electrons zooming off here and whacking into this bit here. Now you'll notice just there that the side of the glass tube's a little bit different. So what happens is when these electrons go here and they whack against that, what they do is they give off the X-rays. Now, the ones that come out of this bit here are the ones that are then used to take the X-rays. So you can see the diagram above, that's what we would call the window. Let's get rid of all those drawings. Alright, so what do? So down this end here, this is where the filament is. We heat it up. So why do we heat it up? Because if we heat it up, the electrons and things start wiggling around, right? They start wiggling, and they get wiggling even more, and then off they come. So heating in here helps the X-rays or the X-rays, the electrons zoom off here and bang into there. All right, and so that's negative charged and that's positive charged, so they'll zoom across and they'll zoom across fast, and that's again the heating makes them vibrate and that a lot more, so they get some energy. All right. Right, so the electron beams zoom across here, bang into that silvery bit in the middle, then X-rays are given off. All right, so what things are missing in the notes? So missing in the notes there above that is the first word is about the filament that is heated. So there's our first word. Filament's heated so that it gives off electrons. And then we've got a positive metal target over the other side. End of the glass tube, and accelerates the electrons over to that tube, bang into there, and the electrons will strike the metal plate, and when they do, that energy they lose that energy, and that energy, which is the other word that's missing, is given off as X-rays. All right. So energy of X-rays. Is the next bit. And so Einstein had his hand in a whole lot of this stuff, and then a guy named Max Planck, met him before when we did matter. They had this theory that, and again we've looked at this, the Photon Theory. And so the Photon Theory, that we used that for when we looked at light and the energy levels and that sort of stuff, when we did matter. But it also applies to any electromagnetic, not just light, that we've looked at. So according to Photon Theory, this energy from the X-rays would be in photons, and so the energy of that photon would be HF. So the energy of the photon, in this case X-ray, H, if we've seen before, that's our old friend Planck's constant. All right, we can look that up if we need it. And then that is our frequency. Now, in this particular case, we're always going to use the Joule second version of the Planck's constant, because that's Hertz, all right? So, and the photon energy is in Joule. So we want the Joule second version of Planck's constant. All right. So there's a couple of categories of X-rays. And the categories of X-rays are soft and hard X-rays. Soft X-rays have a lower frequency. So a longer wavelength. And so they have less, and there's our word, less energy and penetration. And our hard X-rays have, so if they have lower penetration, I should say, then the object needs to be, so we use them for thin objects. Alright, so thin is the other word that's missing. So for hard X-rays, so they have higher frequency, missing word, higher energy, and they penetrate further. So depending on what it is we're going to X-ray, we would use soft or a higher frequency one, or hard ones. So the hard ones, if we want to X-ray through the body, for example, we would need to use hard ones. All right, so that's X-ray radiation. So there's other radiations that I mentioned right at the start were particles, and we've met these before. Radioisotopes. So we met these in when we did our matter. All right, sorry about that. So radioisotopes, they're found in nature. All right, or we can manufacture. All right, and we can do that with what's called transmutation. All right, and we mentioned that before. So under the first one there, so radioisotopes, elements found in nature have isotopes of different masses, different neutron numbers in their nucleus. Some are also unstable and undergo radioactive decay, and those ones are the ones called radioisotopes. And so they're isotopes that decay. All right, so I mentioned about manufacturing and producing them. So how do we do that? So in the early days they used whatever, but now mostly we make them. So because we can control what's going on better. So artificial transmutation is what we do, and that's our missing words there. It uses neutron bombardment. What does that mean? We shoot a neutron at the atoms. All right, so as it says there, essentially neutrons are fired at an element, or fired at an element, and that neutron then, so its missing word, is captured. All right, and so when that's captured, it then creates a radioactive material, and so the thing that we use to do, the machine that's used to do that's a thing called a cyclotron. All right. So an example of that is cobalt 60, not cobalt 6. All right. So we start with cobalt 59, and we plus a neutron that we fire at it, and it's captured by the nucleus, and then we have radioactive cobalt 60. So captured is the word missing. So if we were looking at that, we've got 59 cobalt, and cobalt's number 27, and we fire a neutron at it, and so it captures that neutron and then becomes still cobalt but it's now 60. And by adding that one extra neutron, cobalt 60 is radioactive. Cobalt 59 is not. So here's a little diagram that shows that. Alright, so there's the diagram. Stable cobalt 60, there's our neutron. shoot it in there, gets captured. Cobalt-60 is radioactive. Alright, so in your notes there's a couple of other examples that are used. So technetium, -99 is one that we use. Iodine 131 is also another one that we use. So technetium 99, we use that as a tracer. So it goes around the body through the organs, and then we can scan the body, and we'll get more to do with that. Iodine in particular for thyroid, because your thyroid likes iodine. So if we suspect a thyroid problem, iodine 131, and that'll get collected in the thyroid, and so you'll be able to check and see what's going on there. Alright, so this place called Ansto that's mentioned in your notes is where it's produced. The little machine, if you like, that actually produces these things is about that big, Gentech, and it produces the technetium 99 or whatever. Alright, so there's quite a few videos, a whole bunch of different things on the videos there that give you more information about these things. So have a look at the videos. In chapter 16, there's some questions there on page 10 for you to do. Alright, as usual, anything that you don't understand, make sure you ask me, and have fun.